Hi everyone, today we are diving into the buffer overflow attack using the Seed Labs environment. First, we need to download the zip file of lab setup and we need to extract it so that we can observe two files in the lab setup folder, that is code and shell code. We need to open the code folder in the terminal and we can observe the stack.c program with vulnerability of string copy function. So, string copy is a vulnerability because it does not check the boundaries, allowing us to override the written address on the stack, which means by injecting more data than the buffer can hold, we can hijack the instruction pointer to point our malicious shellcode. That is, we can rewrite the root of the program. So the goal of the level 1 is that to master the fundamentals of hijacking the instruction pointer. In this, we have a 32-bit system with a known buffer size. Here we file. So in that, we need to replace the shellcode with our 32-bit file. In the shellcode, we can find the code for the 32-bit. We need to copy this and paste in our exploit.py file. And to run this, we need to disable ASLR and stackguard with the command. So this command is used to disable the address space layout randomization. That is, by setting it to 0, memory is static, so address is found in the. So by using this command, we are changing the secure shell, that is dash, to ZSH to execute the exploit.py file. And to find the buffer size and the pointer values, we can go to GDB terminal by using the command. So here we can find the vulnerability of the stack.c file. And to find the pointer values, we use the commands. These are the pointer values. For the offset value, we need the difference between. Here we got the offset value of 108 and we will use this offset value in the exploit.py file by increasing it to 4 bytes. And the return address will be, change the return address. We can increase it to overcome the stack value and to execute our shellcode. Now we are going to run the exploit.py file and we need to run our stack. Here we also need to change our start point because we have to overcome the return address and the start point should not be at the low. And we'll run it again. So we have overcome and here we can verify it by. So the EUID is 0 and we have the root access. So this is level 1. Similarly, for level 2, the goal is to learn how to succeed when you don't know the exact buffer size. So we'll almost apply all the logic, but we have no idea of the buffer size. So here we make small changes in the exploit.py file. That is, we have no idea of the buffer, so we comment out the start point, and the remaining values are almost same, and we comment out the offset because we don't know about the buffer size. So now we'll run this file. So here we successfully overcome the level 2 and we can verify it by same method and we have the root access. So for level 3, the primary goal is to overcome the null byte constraint of 64-bit. So for level 1 and 2, we mostly used 32-bit. So here we'll use the 64-bit. So using the same method, we replace the 32-bit shell code with the 64-bit shell code, and the start point would be the 517, which is the exact bytes of the bag file minus length of the shell code. And we'll make some changes in the offset. And as it is 64-bit, we'll make the L equal to 8. Um, and this value changes based on the output. Now we'll run the file. Here again, the level 3 is successful. We can verify it, and we have the root access. For level 4, the level 4 goal is to execute an attack when the buffer is too small to hold the payload. That is, the buffer is tiny. For example, 10 bits. You can't fit a shell code inside a 10-bit hole. So for that, here we made small changes in the return address and the offset based on the goal of our level 4. So as you can see, we can have the root access, and we overcome the and we achieve all the goals of level, 4 levels. Thank you.